All right, and one other thing. Yeah, so we picked up, we'll pick up there. We did the calculation for a monoprotic acid. So in the monoprotic acid, right, that monoprotic means that there was, again, that was this idea of the hydrogen here. There's only one proton on this acid. Okay, so there's only one proton there for the monoprotic acid. In our next example, we're going to look at a diprotic acid. So the diprotic acid just says you have 2 protons. So we're going to call that H2A. So this would be, an example of something like, H2SO4, right, where there are 2 hydrogens, or maybe H2CO3, right? Those would be examples of diprotic acid. So we're just going to call it H2A because we haven't specified which acid it is, okay? So when we do this, we're now looking at the stoichiometry. And we said, if we had just a monoprotic acid, we could basically cheat and use that M1V1 equals M2V2 equation to do our calculation. But here in our neutralization reaction, we can't. And so what we need to do now is figure out basically our chemical equation for this. So a chemical equation with a diprotic acid, so H2A, with water, with sodium hydroxide as the neutralization, right? Sodium hydroxide. Right, so these 2 things react to give you water and a salt. In this case, so the water is going to be liquid, the salt will be aqueous, and the salt is going to be, remember we're swapping our ions, so it's going to be Na2 aqueous, okay? And so on this one, we need to make sure we balance it, right? So if I've got 2 protons here, that means I'm going to have 2 protons means we have 2 waters, right? Because each proton is going to link up with that hydroxide, right? And so you need, in that case, if you have 2 protons, you need 2 hydroxides. Okay, so we can put a 2 there as well. And if we have 2 sodiums, we look over here. On the other side, we have 2 sodiums, and so we should be balanced at this stage, okay? The next thing to do is actually start the calculation. And so here, we're going to take our initial volume and concentration of our base that we use to do the titration, to figure out, so we can figure out the number of moles of the acid that we titrated, or the number of moles of hydrogen ion that we titrated, okay? So here we can say, well, 0.0247 liters, right? We want to convert that into liters, times the molarity, so 0.0967 moles of NaOH per liter. And so the liters are going to cancel out. And I'm just going to do the stoichiometric conversion here. So I'm going to use my mole ratio, where I have 2 moles of sodium hydroxide. And this is the reason you can't use the M1V1 directly, right? Is you have this 2 moles of sodium hydroxide necessary for every 1 mole of H2A, this diprotic acid. And so you'll do that calculation, work through that, and you wind up with a value of 1.194 times 10 to the minus 3 moles of H2A, right? And on this one, you should have 3 sig figs, so I'm gonna underline that 9 there so I can keep track of that as I go. And all you have to do to figure out the original concentration of that acidic solution is take that many moles, so 1.194 times 10 to the minus 3 moles of HA, excuse me, H2A, divide that by the volume, 0.0150 liters, right? We've got 3 sig figs in both of these. And you just plug that in and calculate. That gives you the molarity of the strong, or the diprotic acid solution. So 0.0796 molar H2A. Okay, it's a 6.
Professor, I just had a question. So I found an equation online that you can, for the diprotic, it's M1V1 divided by N1 equals M2V2 divided by N2. Could we use that?
That's the idea, yeah. I mean, that's the whole thing that we're doing. We're just using, in this case, what we're doing is we're using this mole ratio to express that.
Okay, but it's okay if we did it that way?
Yeah, essentially. So this is your M1 V1 over that stoichiometric coefficient, right? And then the stoichiometric coefficient here is just 1, so that it's the same basic idea. Yeah, it's just a different form. So by all means, go about it that way. Just so long as you write it out that way, and you like when you show work, you let me know that that's how you're doing it, right? In case you make any errors, then I can sort of follow what you're doing if I understand what you're doing.
Is that called a diprotic acid equation, or do we need to let you know that we're using that in any way? Or
you could call it a diprotic acid equation. That's fine. It's not really a thing to go about it that way, right? But it's a way of adapting your M1V1 equals M2V2. So that would be fine. So you can say like M1V1 equals M2V2 for a diprotic acid reaction. That would be fine as long as that makes sense, right? Yeah.
Okay, thank you.
Okay. So the next thing I want to do, I actually want to go through something else here. So we're going to keep those annotations for 1 second. I want to go back. So in our reactions, so we talked acids and bases, right, and neutralization reactions, and we identified Arrhenius acids and Bronsted-Lowry acids and bases, right? So something I want to go and do now is I want to talk about sort of the nature before we get into the oxidation reduction stuff. I want to talk a little bit more about this. I'm going to throw in a couple of new slides for us, just some blank ones, to talk about an acid-base reaction from the standpoint of the Bronsted-Lowry definition. So we're going to expand this back out. You guys can still see this blank screen now? Okay. So when we think about a Bronsted-Lowry, get my pen back. So if we look at that Bronsted-Lowry, I'm just going to abbreviate that BL, acid-base reaction. So what we can look at here is, I'm just going to use a very simple chemical reaction for the Bronsted-Lowry acid-base reaction. And that's going to be acetic acid. Okay, that's aqueous. Reacting with a Bronsted-Lowry base. So in this case, ammonia. That's aqueous. And this reaction, when it occurs, what's happening here is the nitrogen, ammonia, is grabbing onto a proton. It's the proton acceptor. So you can sort of think about it as this nitrogen has a lone pair of electrons here, and that lone pair of electrons is going to form a bond with, if you will, with that hydrogen and steal it away from the acetic acid. And so that's going to make ammonium, and you're going to be left with acetate. Okay, so on the reactant side of this equation, we have this acetic acid, right? Okay, so we've got that acetic acid there. And that acetic acid gets deprotonated, right? It loses its proton. Okay, to become acetate. You also have the ammonia, right, which is your base, right? So if we will, I'll label these for you. So base and acid, right? And the ammonia, that base, gets protonated. Okay, and so it gains a proton there. And so when it gains a proton, this product, this ammonium, right, is in itself an acid. And we'll look at that in a second. But basically, if we think about ammonium, it is related, right? These two things are related to each other, right? So you have a base, and the acid that forms when that base gets deprotonated is called the conjugate acid. So that's the conjugate acid there. And when you have the acid that gets deprotonated, in this case, right, we're making acetate. The acetate that's formed is a Bronsted-Lowry base. It can accept a proton, and we'll see the reactions whereby both ammonium acts as an acid and acetate acts as a base, reacting just with water. But that acetate is a base in and of itself, and it's linked, right, to that initial acid by having that acetate as part of the formula. And so the acid has what's called its conjugate base. And we call them, so these are the conjugate components here. So we have an acid and a conjugate base, and we have a base and its conjugate acid. And in these reactions where you have the acid, right, of where you have the acid here, right, that acid is going to react with this base to form these products, right? The conjugate acid from the base and the conjugate base from the acid. Now, if we started out with one of these, just acetate, and you'd get that acetate, so sort of like Maya was just asking as we started class with KHP, right? Where did the potassium go? Well, in a lot of these, if you want to get just this ion, this anion, you'd get it by dissolving something like, in this case, it could be potassium acetate in order to get that to dissolve in water and start with something like this. Or if you want to start with an ammonium in a solution, you would start with it as, say, ammonium chloride or ammonium bromide, so that the two ions dissociate and you're left with this one that's acidic.
We kind of lost you.
Uh-oh.
Yeah, we lost you for like
After you said,
All right, yeah, I just got the message that my connection's unstable. So let's see. So the idea here that we're really getting at is that, well, this conjugate base that comes from the conjugate acid, if I were to get that into solution by itself, how would I do that? I would do it as the salt. So it would be sodium acetate or potassium acetate, where when they dissociate, the thing that acts as a base is this acetate, right? Or if I wanted the ammonium as the initial thing in a solution, I would say take ammonium chloride or ammonium bromide. So let's illustrate how that would work on the next page. Okay. So if we take our ammonium, right, and we want to say, well, let's get ammonium into solution. So let's take something like ammonium. Wow, how'd that changed? How about not the highlighter? How about the pen? There we go. Erase that first. Okay. So if we were to take the ammonium and get the ammonium itself into solution, we would do so by, say, dissolving ammonium chloride or maybe ammonium bromide. When you dissolve that, right, it dissociates into its component ions and gives you, right, ammonium in H4 plus that's aqueous and chloride, right? And the chloride really doesn't do much, right? That's just, it doesn't, so one of the things you'll do in Chem 102 is you'll really start to identify the anions of salts as being acidic, basic, or neutral. And really the chloride is happy not doing anything in a solution. So the important part of this dissociation is this right here, the ammonium ion, which itself is acidic. And it is a Bronsted-Lowry acid. So that ammonium, if you consider its reaction with water, it acts as an acid. So when ammonium plus water react, you wind up getting ammonia and the hydronium ion, right? And so the hydronium ion is actually something we're going to talk about a little bit more in a second, and that's aqueous, okay? Hydronium. Okay, and so this is the ammonia acting as an acid, which is why we call it the conjugate acid of ammonia, right? Water here is acting as a base, right? To form, in this case, we've got our conjugate base, right, for ammonium, and for water, hydronium is the conjugate acid. Okay. Now, hydronium is H3O plus. Okay. What that is essentially the same thing as saying H plus. Okay. But this one has more physical meaning. So it's more physically meaningful. Because the hydrogen ion, it's really attached to a water molecule. Okay, so that's really what's going on there. Okay.
Professor, question. Going back to the slide, if you had a base and water, would the water act as an acid?
That's the next thing that I'm going to get into. I'm actually going to add a couple other slides here, so we
Gotcha.
This is it takes up a lot more writing space than I'm used to. So so let's head back to, so we're back in here, right? So in this case, we have, a couple things, right? We're making this hydronium. Okay. So the hydronium is H plus attached to a water. We notice, exactly, that water is acting there as a base, right? If we then go on and look at our other reaction, right, where we had the acetate, and let's say we want to get that into a solution, we can get that, let's say, as potassium acetate. So KC2H3O2 that's aqueous. That's going to dissociate because this is a potassium ion attached to it. It's going to dissociate into K plus C2H3O2 minus our acetate, right? And the K plus, sort of like the chloride, right? That potassium ion, is basically not going to do anything. It's happy just being a potassium ion by itself. So the important part of this is the acetate ion. And that acetate ion, exactly, Maya, you're right on track, right? That C2H3O2 minus, when that's dissolved in water, it'll react with that water to form acetic acid. And the hydroxide ion. Okay. And so here we have our base is our acetate, right? And that's going to form our conjugate acid, right? Which is the acetic acid. And then the water here is acting as an acid. Okay. And so it's forming hydroxide, which is the conjugate base, which is exactly what Maya's thought was. Well, wait, that means that water can act as an acid or a base. So water, okay, is known as being amphoteric. In other words, it can act as either an acid or a base. And in fact, in a solution of just distilled water, I'm going to try to color code this as best I can. And we're going to do that by drawing some structures. So water, H2O, plus another water molecule, and this is taking place in just distilled water, so we'll call it HOH. So there's our water reacting with another water molecule. What that's going to form is, well, one of them, so we'll say our red one is acting as an acid, and the blue one is going to act as a base, right? And it's arbitrary which molecule you choose here, really. And so what that's going to form now is the hydronium that has bonded to and accepted a proton from the acid, right? Plus, you're going to have the leftover hydroxide from the acid, okay? And that'll have a minus charge, and this whole thing will have a +1 charge, right? And so in this case, this shows water acting as both an acid and a base. So hopefully that helps to sort of illustrate what's going on. And that's a really important reaction, because in aqueous acidic and basic solutions, this is the chemical reaction that's primarily taking place most of the time, and it's the most important one. And when you get into 102, that's one of those things that you have to understand, is this chemical reaction really governs the acid-base chemistry that takes place in aqueous solutions. Okay. And so now we have sort of an idea of, you know, acids and bases and conjugate acids and their conjugate bases as well. Okay. Any questions on that? Yeah, okay. All right, so that gives us a little bit more definitions in the acid-base stuff. We'll be able to talk a little bit more intelligently about acids and bases moving forward, and so that leads us into oxidation-reduction reactions. So with oxidation-reduction reactions, as you can see here, we call them oxidation-reduction, so oxidation-reduction, or for short, redox reactions, right? And what happens is, in an oxidation-reduction reaction, there are two things that happen. Something gets oxidized, right? And something else must be reduced. Okay, and so we're going to talk about reduction and oxidation in a second. But basically, the underlying theme of oxidation-reduction reactions is that the oxidation states of two elements change, right? So there are changes in these oxidation states of the two elements. And so one thing gets oxidized, one thing gets reduced, but what we have to do is figure out what is oxidized, right? What is oxidized? And also we have to figure out what is reduced, and we do that, right, by going and determining those oxidation numbers, like you did in the lab, the nomenclature lab at the very beginning, the very first part of that. And so you've gone through and used rules to determine which of these things is oxidized and which of them is reduced. And so the next thing we're going to look at is our rules for assigning oxidation numbers. So these rules, they are similar to those solubility rules, where rule 1 supersedes rule 2, which supersedes rule 3, which supersedes rule 4, etc. But there's a lot of things that you already know in this set of rules. For example, if you have an element, its oxidation state, so an element, keep in mind, this is for an element, the oxidation state is 0, right? This is something like, any type of a metal, right? A solid, right? Or the diatomic, homonuclear diatomic elements, they're going to have oxidation states of 0 because those oxidation states come about because of charge, right? In the case of an ion, which is the next thing, right? A monoatomic ion has a charge or an oxidation state that is the same as the charge of the ion. Now, we tend to look at oxidation numbers for covalent compounds also that aren't ionic, and that's because they don't share the electrons evenly. And so the oxidation number in a neutral compound, all of the oxidation numbers will sum to 0, or in a polyatomic ion, they sum to the charge on the ion, the overall charge on the ion. And so it essentially gives us a pseudo charge on a given covalently bound atom. And so if you have something that is, a group 1 metal in a compound, so an alkali metal, it'll have a +1 charge just like +1 ions do, right? And so we kind of think about interchangeably almost. It's not really interchangeable, but we kind of shorthand it as charge and oxidation number are the same thing. And we'll go through some of these calculations here in just a minute. But if you have an alkaline earth metal, it's going to be a +2. So we've already learned a bunch of these rules, okay?
Question, Professor, is this table 4.2 on page 143?
Yeah, I believe so.
Because there's
It's
only like 5 and you have 7 rules.
So it's similar to that. Okay, so there
Okay.
are lots of different oxidation number tables out there, or lists of rules. Some of them are more complete than others. Some of them go about it in different ways than others. They all are meaning to help you determine those oxidation numbers of the elements in the compounds. So there's some might use, I think the one you did in the lab used like 9 rules or something like that. So it can vary a little bit here and there. Okay.
Do we need to memorize this?
This is something you need to know. This is something you need to be able to figure out quickly. And largely, you know a lot of these things. Like we said, the oxidation number of something that's an alkali metal is going to be a +1 if it's in a compound. An alkaline earth metal is going to be a +2 if it's in a compound, right? So we know that because of how we started to learn the periodic table, right? Oxygen, we know, is going to be -2, except if oxygen is bonded to fluorine, it's going to be a +1, right? If oxygen is part of a peroxide, right? So H2O2 would be a peroxide, right? Hydrogen peroxide. That right there would be an example of where oxygen is going to be a -1, right? So these rules, we're saying, well, usually oxygen is -2, except when it's bonded to fluorine or when it's bonded to a hydrogen in a peroxide. Some other ones, right? The oxidation state of hydrogen is usually +1. The only time it's not +1 when it's in what's called a binary metal hydride, which is something like sodium hydride, NaH, right? And sodium hydride is going to have a hydrogen, that is a -1 charge. And that's something we'll have a better feel for why this is as we get into the beginning of chapter 8, as we start to study electronegativities and the pull of an atom on the electrons in the bond, okay? So rule 7, the oxidation number of fluorine is always -1. So if I wanted to make this list longer, I could have put that up sort of, you could almost think about that as superseding, rule 5, right, between rule 4 and 5. It's more important, right, but we already account for it in rule 5, so we don't have to worry too much about it. But chlorine, bromine, and iodine usually have oxidation numbers of -1 also, unless they're combined with oxygen or fluorine. And again, that's going to come back to the electronegativities that we'll study more at the beginning of chapter 8. So you
Professor, sorry, I have one more question. So when we did that nomenclature lab, on the periodic table, we had like -1, -2, -3, -4, all those groups.
Mhm.
Can we still use those rules even though you don't have that on your list? Like, is bromine still a negative? I'm sorry, boron still -5, and carbon -4?
No, so with things like carbon and boron and a number of those elements, sulfur, phosphorus, nitrogen, they're going to have oxidation numbers that vary because these 7 rules that are on here are going to supersede those. And generally, we're going to deal just with compounds that have hydrogen, oxygen, fluorine, metal ions as part of the compound. So these rules will get us through most of the chemical compounds that we work with. That being said, when we start to look at the electronegativities later on, you'll be able to, just based on the electronegativity value, which we have an electronegativity table in our equation sheet, based on that electronegativity value, you'll be able to determine which of the 2 bonded atoms is going to essentially be assigned the electrons and have the negative charge versus have its electrons taken away from it and have a positive charge. So those rules are somewhat there, but they're superseded, like for the rules for a given column in the periodic table aren't set solid rules except for the ones that are in this list of rules for assigning oxidation numbers.
So kind of like a rule of thumb is use the 7 rules first and then possibly use the periodic table rules that we use for nomenclature, but we may not have to use them.
That's right. Yeah, because most of the things that you're going to encounter are going to use these 7 rules. Now, these 7 rules are kind of embedded in those to some degree. There's just a hierarchy of those charges. For example, right, the hierarchy to think about, right, we usually think about oxygen as being a -2, right? But in reality, if it's bonded to fluorine, right, that oxygen isn't going to be a -2, it's going to be a +1 because the fluorine is actually going to pull its electrons away. So the fluorine rule supersedes the oxygen rule in that case, right? So hopefully that makes some sense. Yeah, Caitlin.
Sorry, I saw the Andrea's options. Around, so I wanted to see if that actually works, like selecting that raise hand option.
Yeah, cool.
Yeah, no, I just didn't know if you did.
I don't, yeah.
I get familiar with this. Like, so if you select the share screen and then you, on the right hand side, you can select raise hand or lower hand. That's not the lower hand.
I'm sorry, you're breaking up a little bit with your sound.
Sorry, you can, like, you have the option to raise your hand. I just wanted to make sure that you have set the notification so that I'm not raising my hand.
Oh yeah, it definitely popped up on the screen. That was actually really useful.
Around, I don't.
Okay, well, thanks. All right, so does that sort of clarify how these rules are used initially? Hopefully. All right.
Yeah.
Great.
I have a small question. It's actually more of a using Zoom. How did she raise her hand? Because one thing that I really don't like is interrupting your lecture.
Okay, so Kaylin, do you want to would you mind typing into chat? I'll give you a couple seconds before I move on, where to access that.
I appreciate it. Thank you.
So I can just type it in chat as well, but just so you can continue the lecture, what you do is if you move your mouse and have the mouse hover over, sorry, if you raise your mouse and have your mouse hover over the screen, the main screen, you click the option share screen, or wait, sorry, no, you click the chat option, and then a window is going to pop up on your right hand side, and on the bottom right it's raise hand. Do you guys see that?
I have, if you click on participants, then
Yeah,
you find.
there we go. Yeah, for me to get to participants, I have to click on like chat or something. So
Yeah, I'm not seeing that on mine, but hey, I see 2 hands raised. So
cool.
So for some
Thank you
people,
very
it
much.
might be that you just click on more, and then it has chat, meeting settings, raise hand, disconnect audio.
Now, Professor, do you
I
want
have
us
to
to
click on
do that?
participant. Yeah.
yeah, that'd be fine if you want to get my attention. I'm okay with that. As long as it's, we're not having like loud conversations and we can hear the lecture, I'm okay with you interrupting me here and there too. But that's a really easy way to do it too. If you can have that question, then that'll totally stop me really easily. Because it pops up in my upper right-hand corner and I can see that and respond to you.
Yeah. And just a heads up, you guys, you have to lower your hand as well. You can't yeah. So.
Okay, cool. Thank you guys. That's great. All right, so let's take and utilize our oxidation number rules to determine the oxidation numbers of each of the elements in this chemical equation. Okay, so we're going to use our oxidation rules to do that. So if we go back up to this page, we know that the oxidation number for a free element, right, rule number 1, is going to be 0. So when we have zinc here, it's going to have an oxidation number of 0. All right, so that's a free element by itself because it's not sharing electrons with anything. But when you go to look for the copper sulfate, you've got 2 parts to this. Yes, Maya.
Does rule number 1 supersede rule number 2, and so on?
Yes, absolutely. And so here for the second compound, we've got 2 parts to it. We've got the sulfate, okay? And you can think about the sulfate as its own polyatomic ion. So overall, we know that sulfate, right, is SO4 2-, right? Which means the copper is going to be an ion, right? And so if sulfate is a 2- charge, so that copper has to be a +2 charge. But you can also determine the oxidation number for oxygen and for sulfur. And so for oxygen, what you know is the number of sulfur atoms, right? So you have 1 sulfur atom times its oxidation number. So the number of sulfur.
He was giving his address.
Is somebody?
Yeah, I'm right now. I'm in the class. I'm learning online.
Okay.
Okay. Thank you. I call you back.
Zimadu, go ahead and mute your.
Sorry, sir.
That's okay. All right. So the first part of this, right, is the number of sulfur times the oxidation number. I'm going to abbreviate ON of sulfur. Plus, so we're looking at this, right? So plus the number of oxygen times the oxidation number of oxygen will equal the overall charge on the ion, right? And so in this case, if we go back to our list of rules, we'll find that based on rule number 5, right, oxygen is going to be -2. Okay, so we go back here and we say, okay, oxygen is -2. Okay, well, -2 times 4 is going to be -8. So this -8 plus whatever sulfur is, right, is going to equal the -2 charge up here. Okay, so sulfur has to be +6 in that part. Okay. Now, if you ever see a sulfate, now you know the sulfur is +6 and the oxygen is, each oxygen is -2. Which means if you, and the other thing is if you have a sulfate, you know the zinc is going to be +2 here because it's in the compound zinc sulfate, and so those charges are going to add up to 0. And then over here we have copper. It's in its elemental form by itself, and so it's going to be a 0. So I'm going to go and circle each of, or square, put a box around each of the oxidation numbers for each of the elements in this chemical equation. Yes, Amir.
Does the oxidation numbers have to be always equal to each other on both sides? I'm not talking about each element or each compound, but in general. For example, here we have on one side, we have 2, 6, -2, 0, and the other side, the same thing. Will it always happen like this?
No, it won't always happen like that. In this particular one, this is a very simple oxidation reduction equation. And so in this case, it does. We're going to actually see in another example that it doesn't always do that. Okay,
Thank you.
Yeah, well, and so there are going to be lots of potential examples for this going forward. Okay, but what we want to do here now is identify what is oxidized and what is reduced. And so for understanding what's oxidized, right, the thing that is oxidized is losing electrons. So oxidized means it's a loss of electrons. So we've got 2 mnemonics here. In each mnemonic, it expresses that oxidation is the loss of electrons. And the reduction, okay, the reduction is a gain in electrons, right? So the reduction is going to be a gain in electrons. So our 2 mnemonics, so oxidation is loss or oil, and reduction is gain or rig. So oil rig notation is one way to express that. And the other one is Leo-Gur notation, which we kind of think about. So loss of electrons is oxidation, or gain of electrons is reduction. Whichever one of those helps you remember, use that as a mnemonic to do so, right? Oil rig makes sense because oil rigs are things. Leo-Gur makes sense because, well, the astrological lion is Leo, and of course we all know that the sound that lions make is grr, right? So you can use that if you, or whichever one sticks out better to you, okay? But now what we can do is we're going to use what are called tie lines, okay? So tie lines, ooh, what happened? Doing it again. How about the other way? Tie lines. This is not helping. There we go. Need a bigger screen here. So tie lines are as follows. If you look for the oxidation numbers that change, for example, zinc changes its oxidation number from a 0 to +2. If it goes from 0 to +2, the charge essentially has changed. And if the charge goes up, it means it's lost electrons. And so we mark that as either Leo or oil. Okay? So it's lost electrons, its oxidation number has gone up. If you look at the copper, right, we're going to use a tie line for the copper. The copper's oxidation number has gone down. Its oxidation number has been reduced. That's where reduction's name comes from. And so we can label that as Gur or rig. And so right there, we've used our tie lines and the oxidation numbers to identify the elements that are being oxidized or reduced. Okay, and with that, we're going to stop there. And on Monday, we'll pick up with the rest of this and talk about oxidizing agents and reducing agents and start to look at some other complex examples of oxidation reduction reactions. Okay.
Wait, can you go back for a second?
Yes.
Thank you.
So basically, we've just scratched the surface of oxidation reduction reactions, and we're only going to scratch the surface in this course. Again, there's a full chapter based called Electrochemistry in a Chem 102 section where you'll really dive into it more deeply. And we will spend a little bit of time, I'm still planning on doing potentially doing a lab where we do the balancing of much more complex redox reactions, and we'll use a whole lab period to do that. And that'll be something later on, okay? And again, these lecture slides, I'll post these up on Canvas, and hopefully by Monday, I'll have lectures slides and the recorded lectures posted on onto YouTube, okay? All right, so with that, I'm gonna stop our share. All right, and we will end our lecture